type and type mode of Coq. It contains the following type constructors. So this is a complete list of type constructors that UniMath contains. So there is dependent product, unit type, dependent sum, empty type, disjoint sum, booleans, natural numbers, identity types, and the universe. So in particular, it does not contain any other inductive constructions of Coq or co-inductive. So it's a very small subset taken into account how many inductive types usually one uses in Coq formalization. So this outlines the first component of the UniMath of the foundation. Now here is an example of the UniMath code. In these lines we define the type of categories from the type of pre-categories. The meaning of these two concepts we will discuss in a few minutes. So this is actually a screenshot from a GitHub page, and so it goes definition what it means for a pre-category to have home sets, so to have sets as objects of morphisms. Then there is a proof that this is a proposition. That's something which we are going to talk about a little later. And then there is definition of a category as a pre-category that has home sets. And then there is a bit of a technical stuff below it, which allows to work with this concept conveniently. So there are access functions, as we call them, and projection, which allows one to consider a category as a pre-category. So this is a very concrete example, and from this example, I want to show you that one can read it. It's not something which is not readable. It's readable, and we read each other's code all the time. And we work sometimes on making the code more readable. So a code is not something which you write once so that it works, and then it sits in the kind of assembler format or in whatever format which you cannot really access. A code here is something which you write with a clear intention that other people are going to read it and reread it and reread it. So it's a very different from computer code in the usual sense. It is much more similar to how we write a paper, with an additional complexity arising from the fact that other people may not only read it but may also suggest improvements and modify it, and so there should be certain control of how it can be modified, for example. So if we don't use the resizing rule, now this is a part of UniMath that we will discuss later if we have enough time, but it's a whole separate story. And I ask for permission to hide it for now, just because we don't have enough time to go into it. It's a very interesting story. So if we don't use the resizing rules, then we believe that we know how to interpret any construction of the UniMath as a construction where types are type expressions define can-simplicial sets. Elements of types are defined points in these sets. Elements of the identity types are defined paths between the corresponding points. And the universe is the can-simplicial set, which is the base of the universal confibration. So this is the second component. If going back to foundation having three components, so we discussed the first component. Now this is the second component This is how to interpret the primitives in the mathematical world. So now I say we believe that we know how to interpret. So the element of belief here comes from the so-called initiality conjecture, which is a technical thing which we hope to prove in the foreseeable future. It actually applies to most type theories, not just to UniMath. So with some experience, one can learn to automatically see the UniMath sentences as referring to such objects and use geometric intuition to construct proofs. So when I read a UniMath sentence, I almost always can parse it and understand what kind of geometric homotopy theoretical object is behind it. That was the initial kind of breakthrough in this whole development, that I learned how to mathematically interpret. It actually applied to all sentences of Koch at some time, and that gave me for the first time understanding of how it can be used, how it should be used for mathematics. So this outlines the second component of the UniMath as a foundation. Now we need to say a few words about the third component, the collection of constructions that, using the interpretation of the primitives, defines formal counterparts of the main mathematical concepts. So we have these primitives. They are interpreted as consequential sets, points, paths, and the base of the universal consequential set. And how do we use these gadgets to define what are real numbers or what are smooth manifolds? So sometimes I use the word univalent type theory because these constructions actually appear not only in UniMath but in all other univalent foundations based on dependent type theory that I know of. So the first, it's this path from these primitives to the world of mathematics as a whole. That is what is most kind of this is one of the most important parts of univalent foundations. So when one say univalent foundations, this path is a very important thing. In inventing it, it was that's what kind of proved for me that the whole thing can work. So the starting point here is the concept of a constructible type. So constructible from homotopy theoretic perspective. So we will be building this correspondence such that it's homotopy invariant. That anything which the two things which are homotopy invariant are indistinguishable. So the first most important part is the most important definition, which took some time to come up with, is constructible. It means what it means for the type to be a one-point, to correspond to a one-point set. So we want to define what is a one-point set in the univalent foundations. And this is a definition of one-point set. It's a type together with an element in this type built out of it is contour T. So path here is the identity type from T1 to T0. An element of is contour T is interpreted as a proof that T is constructible. So as a proof that T is a one-point set. in the simplicial set interpretation, is-quanter is a consimplicial set that is non-empty if and only if the simplicial set corresponding to T is contractible. And in this case, is-quanter T is also contractible, which is an important fact. So we know what is a one-point set. Now the next thing which we want to know is what is its set, a general set. How to define a general set? Well, it turns out that there is one thing between one-point set and a general set, which was unexpected, but it is there. So, so one goes in and defines something called H-level by induction. So H-level 0 means contractible, and H-level Sn, where S is the successor, 1 plus n in Koch, H-level 1 plus n means that for every 2 points, the identity type between these 2 points is of H-level n. Now, in the simplicial set interpretation, types of H-level 1 are either contractible or empty, and thus they correspond to truth values. So types of H-level 1 are called propositions. Types of H-level 2 in the interpretation are exactly consimplicial sets homotopy equivalent to sets. So types of H-level 2 are called sets. Types of H-level greater or equal than 2 also often called n-2 types. So a set would be called 0 type, a next level would be called 1 type, and so on. Sometimes one also uses -1 types to refer to types of H-level 1. So we know what is a one-point set. Then after that goes truth values or propositions, and then after that go sets, and after sets go types which don't exist in set theory, which correspond in a sense to collection of objects which have automorphisms. Like the collection of all sets in a given universe is a type of H-level 3. And a collection of all types of H-level 3 in a given universe is a type of H-level 4. This, of course, requires proofs. Now, after we have H-levels, another thing which we need is to define what is an equivalence. So we start with the notion of a homotopy. So if we have two functions, f and g, so functions are primitives because we have the concept of a dependent product, which in the case when dependence is trivial becomes the function type. So the function type is the primitive of the language, and so if I have two functions, then I can define a type of homotopies between these two functions is a type of families of elements of identity type types given for all t in t between f of t and g of t. So a fiber or h fiber of a function f over a point is defined as you would define a fiber. What is a fiber? A fiber is a collection of elements whose image is equal to the given point. So that's precisely what's written here. It's a collection of pairs, an element together with the proof that its image is equal to, or rather together with the path from its image to this point. And that turns out to work both for the obvious intuitive definition of a fiber when we restrict to sets, and also for the definition of H fiber when we work with types of higher H levels. Now we have two definitions. We have many definitions of equivalence, but there are two which I would call basic ones, at least from the UniMath perspective. So there is a naive equivalence between types T1 and T2. So it's a quadruple, F1, F2, H1, 2, H2, 1, where F1, F2 are functions going in the opposite directions, and H1, 2 and H2, 1 are homotopies of the corresponding compositions with the identity functions. So so if I just have two functions in two directions, that's what corresponds intuitively to the concept of homotopy equivalence in books about homotopy. But here we actually have to consider the type of these quadruples, and it turns out that it's not the right thing in a sense. So that's an interesting one of the first kind of places where one needs to prove things. So one defines an equivalence instead as a pair FW, where F is a function T1, T2, and W is an element of the type which proves that F is an equivalence. And this type is just a product of types which tell that all of the H fibers are contractible. So we define what is an equivalence as a function whose fibers are contractible. And then there is a very important it's called a theorem, but it's actually a construction called Grad theorem. It has a history, which says that given a naive equivalence, we can construct a true equivalence. So there is a function mapping from naive equivalences to true equivalences. There is, of course, also functions from true equivalences to naive equivalences. And basically what happens is that true equivalences form a retract sitting inside naive equivalences, and this retract is the good object to work with. This type of weak equivalences, it participates in the univalence axiom, so which is of extreme importance in this whole field. And the thing is that if one tried to use naive equivalences instead in the univalence axiom, then the result would be an inconsistent system. So if we had more time, I could explain where the difference between the naive and non-naive equivalences lies, and it's related to the concept of H level. So the foundations already on this level of very, very basic objects is how to say it, involved in a good sense of the word. So there are already dependencies between statements and properties which are not immediately obvious. And there are already some definitions are restricted. One cannot just pick up any definition which comes to mind, because then things don't work. One actually has to be very careful already here, and when one is careful at this level, then one ends up with this way of defining major classes of mathematical objects in terms of the univalent foundations, which then works very well and allows to do a lot of things in kind of expected expected fashion, I would say. So that was a piece of univalent foundations. It is found in the files called basics in the UniMath. And these are files which go back to 2010 when it was all just starting, and we didn't have to change anything there since then. So I mean, we added some things and edited for better readability, but it remained what it was, despite, I mean, after a lot of use, and it's a very reliable foundation. Okay, so after this, necessarily brief explanations of the UniMath as a foundation and of the implementation of the UniMath formal deduction system in Coq, let me pass to the main topic of the lecture, the UniMath library. So I will attempt to give a feeling about this library by giving examples. So instead of giving kind of a table of content, I will give examples. And I think you can find slides by Benedict Arends and Catherine Lelay from the last week, where the UniMath is represented in a more kind of content-like way, so where you can see what is there and what isn't. So UniMath library today grows in two ways. So there is a part of some growth is directed and some growth is independent. So the directed one comes from one of us. If somebody comes and says, I would like to study and I would like to learn UniMath, we can give study tasks, and study task would be something which we actually need for the future development, just which was missing yet, which is yet missing in the UniMath. So this is the directed, or maybe some of us who know UniMath well also can. Well, no, okay, this is the directed. Sorry, I was confusing myself. So the independent is suddenly we get a pull request, so a submission to the UniMath from somebody we never heard about, and it is interesting. And somebody comes in and starts formalizing something which he or she is interested in formalizing. So this is the second way. So two examples of the second kind are the work of Tommy Panilla, who has formalized the part of theory of triangulated categories. He was a very mysterious person. We didn't know where he's from, or we didn't know anything about him. Well, and the work of Anthony Board, who is formalizing the theory of modules over rings and some other things. Anthony we know. So another example of the second kind is the work that Benedict, Arends, Peter Lamsdane, and myself are doing on developing and formalizing the theory of categorical structures of type theories in univalent foundations, and more about this example later. So now here are some examples of the first kind. So there are two study tasks that were done by Matthew Weaver, a graduate student in Princeton, who's actually here. So one of the first problems, we didn't have this, so we needed a construction for this problem, The problem was as follows. Let H set be the category of sets. Given a set S, to construct an equivalence between categories, the slice category H set over S, and the category of families of objects of H set parameterized by S. So the category of functors from S to H set, where S is considered a discrete category. So if you think a little bit about it, you'll say that it is kind of more or less clear that it should be true, that families of objects parameterized by a set, families of sets parameterized by a set are kind of the same in categorical sense as sets over this parameter set. So now here interesting things are happening. The category theory in UniMath is interesting. So there are 3 different types of objects corresponding to the concept of a small category. There are pre-category, category, and univalent category. So basics of the category theory in the univalent foundations can be found in the paper by Arendt, Kapulkin, and Schulman, Univalent Categories and the Rest Completion. So a pre-category is what you get if you try to define a category in type theory. So you say, okay, I have a type of objects. For every 2 objects, I have a type of morphisms. For every 3 objects, I have a function of composition, and then for every object, I have an identity morphism, and then I have 2 axioms related to identity, and 1 axiom for associativity. So if you just do that, what you get is called a pre-category in the UniMath. Now, a category is a pre-category where types of morphisms are sets in the sense of univalent type theory. It turns out to be very important because if you think about it, then you'll discover that things like two categories well, there are many kinds of 2 categories, but many 2 categories are also pre-categories if you forget part of the structure. But there are not generally categories in this sense. So it turns out that pre-categories appear in other parts of the of mathematics, and they do not necessarily correspond to categories. So a category is a pre-category where types of morphisms are sets. And univalent category is something a little bit more complex. Is a category where the type of isomorphisms between 2 objects is equivalent to the type of paths between these 2 objects. So between for the type of equalities. And when we were just starting learning the world of univalent foundations, we kind of thought that that univalent category is the correct definition of a category, and everything else is just shouldn't be there. But the more we worked, the more we understood that all 3 of them have their place in the theory and in the library.
You can speed up a bit. You can speed up a bit if you want. So you have about 20 minutes.
Yeah, I see. Yes. Well, we're not supposed to go to the very end. I mean, it's not expected.
But we do want the punchline.
Well, there will be a punchline, but it probably totally not what you think. So types form a pre-category. Sets form a category. If we add the univalence axiom, then we can prove that the category of sets is univalent category. Now, math construction to this first problem is given in here, and it uses a univalent definition of a set. However, the problem can be reformulated for all types, and I don't know if there is an equivalence in this more general setting. So that's a question. Now here is a second problem, considerably more involved. Let's take a pre-category and a pre-sheaf of sets on it, and let this be the category of elements of P. So these are pairs of an object of a category and element in P of this object. And morphisms are morphisms between objects of the category that respect these elements. So to construct an equivalence between this pre-category and the pre-category of the slice pre-category of pre-sheaves over P. So this is used very extensively in type theory, because the thing is that well, when one wants to the slice if you have pullbacks in a category, the slice pre-category, you can pull it back, but this pullback is not functorial. So you cannot form a pre-sheaf of objects over a given object, because the pullbacks will not satisfy the pre-sheaf actions. So it is resolved, because such pre-sheaf is really convenient in many cases. It's resolved by the use of this construction. So one replaces the category of objects over a given object by this category. Well, one works in pre-sheaves, and one replaces it by this category of elements, and the category of elements turns out to you can pull it back in a strictly functorial way. So from categories of elements you can form a pre-sheaf, and this is the basis of some important constructions in when one wants to build various models of type theory. So we didn't have it, and Matt did it, and it's here, and it actually works for all pre-categories C. But it's important that it's a pre-sheaf of sets as opposed to all types. So now the next example is a much more complex thing. And it's, I will just kind of show you how it looks. I will not really expect you to read into it. So it's at the center of our recent paper, Categorical Structures for Type Theory in Univalent Foundations. And it can be found in the type theory, which is the second repository of the UniMath GitHub organization. So this definition is something which I probably want to explain. At least to some of us, it might be interesting. So a split object extension structure is such a kind of almost trivial thing. So it's a functor. Well, actually, it should be ty is the name of the functor, and this is a mistake here. So it's a contravariant functor from C to H set called ty, so a pre-sheaf of sets. And then for every gamma in C and A in ty of gamma, one is given an object of C and a projection from this object to gamma. So it's like one takes the definition of category with families or something like that, and just takes one very small part out of it. And it doesn't look like anything useful, but it actually turns out to be useful as soon as one actually starts doing proofs. It's remarkable how many actually interesting structures, mathematical structures, come to the surface when one starts working on detailed proofs. Something which you would never think about otherwise actually turns out to be useful and to create beauty in the proofs. It is very, I think, important. It's very important that mathematicians forget about the fact that mathematics is not about theorems, it's about proofs. And when we remember about it, then new mathematics comes to our attention. So there are some annotations here, which you may see later if you want. And so now if I have a category with an object extension structure, I define two different structures on an object extension structure. One is called the factorial term structure, and it's given by this. And one is called a split Q morphism structure, and it is given by this. So of course we formalize this and we formalize that. And then we consider the problem for a category C and a split object extension structure X on C to construct an equivalence. To construct an equivalence between term structures and split Q morphism structures, between structures of these two kinds. And there is a construction in outlined in the paper and formalized in UniMath. Now, there are two interesting things about this construction. First of all, it does not work in set theory. So in set theory, if I take the set of structures of this first kind and the set of structures of the second kind, they are not bijective. There are very simple examples which show that the sets are not bijective. The reason that the types are equivalent arises from the fact that these types are not sets, and from this additional structure on them, which makes them essentially groupoids. So they are equivalent as groupoids, but their sets of objects are not equivalent. So this statement is essentially uses essentially types of H level 3. And then the reason for our interest to this thing is that the type of categories, the type of structures of a category with families is easily shown to be equivalent to the type of pairs of an object extension structure and a factorial term structure on it. And the type of structures of split type categories is easily shown to be equivalent to a pair of object extension structure and a split Q morphism structure on it. And so that equivalence which we did there provides an equivalence between types of split CW structures, CWF structures on a category, and split type category structures on this category. And it opens up a way to study these structures in the univalent foundations. So that was an example of something we do, something we can do, and something we actually do with UniMath, and something which is actually well, in new mathematics in a sense. I mean, people have been saying for ages, not for ages, but for a reasonably long time, that these two kinds of structures should be equivalent in some sense, but no one ever formulated it or proved it. So it is new, leave alone the fact that how it looks in the univalent foundations is even more interesting. So as I have 10 minutes, right? So actually doing well. So and as I have mentioned, it's impossible to fully predict the directions. So this is the present of the UniMath. That was my present part, and now I can go into the future, and it's as always about the future. It's much less. I don't have to be as precise as about the present. So I mentioned that it's impossible to fully predict the direction in which the UniMath will develop in the future, because an important part of the UniMath development arises from new participants with their own ideas. What I can outline are the directions that I see as interesting and important, and whose development has either already started or is expected to start. So the first direction is this direction which I ended my presentations about the present on. It's the direction of the development and formalization of the mathematics surrounding the study of syntax and semantics of dependent types. It now branched into several sub-directions. The most clearly aimed among those is the one whose goal is to formalize the construction of the univalent simplicial set model, because it has a concrete goal, and its development progresses well. In one branch, it calls for the development of a two-category library in the UniMath, which we don't have. There are two approaches to two categories. It's either two categories, a pre-category with pre-category structures on the types of morphisms, compatible with what they need to be compatible, or a two-category, two pre-category is a type with a family of pre-categories of morphisms where compositions are functors. So we have a library started by Mitchell Riley using the second approach. There are some considerations suggesting that the first approach may be more convenient for various purposes. So it's likely that we'll have two branches which will weave together and to have a common development. So, by the way, this this immediately opens up the study of homotopy two types in the UniMath, because the rest completion of an algebraic groupoid, two groupoid, will provide the two types. So we'll have access to all two types then. So another direction is the one that I have stated in my Bernal lectures, is to formalize a proof of Milner's conjecture on Galois cohomology. So it hasn't been developing very much. On the one hand, I discovered that formalizing it classically is not very interesting to me, because I'm quite confident in that proof and its extension to the Bloch-Kato conjecture, and just taking it and formalizing it as it's written is kind of doesn't seem to be worthwhile at the moment. On the other hand, when planning a development of a constructive version of this proof, one soon encounters a problem. So it's very now a constructive proof of this theorem is a much more interesting undertaking, and I can see how it may go, and I see that many things can be done, but it hits one problem, that the proof uses so-called Merkuriev-Suslin transfinite argument, which relies on the Zermelo ordering theorem, and which in turn relies on the axiom of choice. Now, there has been attempts to avoid this argument since the very first proofs of by Merkurjev and Suslin in the early 1980s. However, it remains an open problem. It is an open problem in motivic field. Solving this problem would be very beneficial for the whole field also. And the interest in it is now increases, and we may hope for some progress. There are some ideas of how to do it. So until then, we can develop UniMath formalizations of other components of the proof, but the proof in its totality will remain out of reach for constructive formalization until that problem is solved. And that is, I mean, it will require, as far as I can see, the total rerouting of the whole proof through a different path. And it's quite interesting, and there are people who Suslin himself refused to think about it. I called him and I said, Andrei, there is this problem which I would like to work on, and or if you would like to do something about it together. He said, Volodya, I have tried to do it so many times. No, I'm not going to do it again. So it is something which people know about and care. So finally, there is a third direction that I think UniMath can and should develop, and it's direction towards the modern theory of geometry and topology of manifolds. So there are some reasons why this direction, which are kind of social, but the first step in this direction would be a definition of a univalent category of smooth manifolds. Univalence will force all the construction relying on this category to be invariant, or maybe better to say equivariant with respect to diffeomorphisms, which brings us again to problems open in the field. No one knows how much of the theory of smooth manifolds can be developed constructively, which creates an additional challenge. At the end of the lecture, and I'm actually going to have a few minutes for questions, I want to acknowledge the extremely important role that the Koch development team played in the recent years in the successes of the UniMath. Koch today is faster and better than it was a few years ago, and without this program, building UniMath would be much more difficult. Thank you very much.
Andy Pitts, University of Cambridge. Could you just say something about your personal position on constructivism? I mean, so you've mentioned some things where we have classical proofs, but we don't yet have constructive ones. So, as a mathematician, why do you care about having a, say, constructive version of some particular development?
I was taught to care about constructivism in the last few years through my interaction with people whom I respect very much and who are constructivists. And so I began to see myself constructivism as something which is in a sense more general than the classical mathematics. So I see classical mathematics as a subset of constructive mathematics today, and a very important subset, because going there, it's kind of, there is a projection and there is an inclusion. So it's kind of a retract, which going to this retract simplifies a lot of things. So it does make sense always to try to do something in a simple way first. But ultimately, of course, kind of provably non-constructive existence proofs do leave some sort of emptiness in you. if you can prove that you have proved the existence of something which have provably cannot be constructed, then what does your proof mean? It's a complicated and interesting story, and I hope to one day to give a talk about it, but I don't think I'm ready yet.
So let's start with Jeremy and then Bas.
So Jeremy Avigad, Carnegie Mellon. So you mentioned this problem, which to formalize you would need a constructive proof. Do you think the UniMath library and formal methods can be helpful in finding such a proof? Or does it really have to be done independently on paper first? And then
it's a little, in that particular case, there is this rerouting issue, which doesn't have anything to do with formalization. It's kind of rebuilding the whole structure of the proof. But ultimately, of course, the formalization in the UniMath is the proof that it can be done constructively. Otherwise, any argument saying that it can be done constructively, to me, would feel a little incomplete. But I don't think in that case it can really help. But I don't know.
So Bas, then Martin here.
Bas Peppers, University of Aarhus. I have an answer and a question. So the first one is you raised the answer about the question about the equivalence between slices and families. So this is something that we've already published in the paper with Egbert Reichendt. So this is what we call the object classifier, and it's an important step into what the program that we call synthetic higher topos theory that also Egbert Reichendt talked about last week.
So you constructed it for all types as opposed to...
Yes, and it can actually be generalized, and this is in our new paper with Mike Schulman, to all modalities. So there's actually a complete story about these things.
Okay, I'm okay. Modalities are interesting, but first of all, the main modalities, so to speak.
The main modalities are included. Yes.
Okay.
The question I wanted to raise was in Tom's last lecture, he presented the challenge of formalizing sheaves and stacks.
Formalizing
sheaves and stacks.
Yes.
So is this a place where univalent foundations would be very useful?
I see. I mean, a considerable part of this theory should be formalizable in the UniMath. I mean, we do have pre-sheaves, and we do have a lot of stuff about pre-sheaves. So it's a matter of formalizing Grothendieck topologies. And I think it can be done. I don't see any immediate problems. I mean, I don't remember anything there which would use axiom of choice.
Yeah, I'm Martin Hoffmann from Munich. My question is whether, leaving constructivism aside, you have suggestions for like theorems from, say, homotopy theory or algebraic geometry, which would be worth of formalization. You said that one of yours was not worth, but which ones are worth?
Well, you mean non-constructive formalization?
Yeah.
Specifically. You know what? I don't think the motivation here can come from me. But I easily imagine someone who will come and say, I think it needs to be done, and we'll do it in UniMath. I mean, UniMath is fully, you can use it for non-constructive mathematics. It's just that at the moment I don't have any kind of burning desires to formalize something non-constructive.
I had a question regarding your views on automation. So last week you were saying that you want the proofs to be almost entirely handwritten, and there are two directions in which we're seeing automation go. One is actually automating the steps in the proof, and the other is these the computer heavy, computation heavy proofs themselves. So what's your take on the automation in general?
So I would be very happy if I could use something like a computer algebra package inside UniMath. Then it will have to be included into this. Then it will have to be formally verified at some point itself. But then the code needs to be too. So, but I think it would be good to have certified complex computations available to the person who is trying to prove something. I think it more concerns the logical structure of the proof, where I kind of draw the line.
So you want those steps to be plausible and
I want them to be the proof to be such that one can read it and see these steps, the structure of the proof for himself or herself.
Any other questions? Okay, let's thank Vladimir again.
Thank you.
You want to tell us about that?
Okay, just thank you. So some of you might like to follow the Institute on Facebook or on Twitter. Just to show you, we've already got a couple of tweets up already about your program. And there is the hashtag BigProof. The only thing I shall say about that hashtag is also associated with the wrapper that M&M. Your mission is to out-tweet M&M's collaborative wrapper. That's my challenge to you all. Just for amusement, to show you. So let's go for latest at the moment. So
And I think he has priority over this.
Currently he does, but we can see if we can talk.
I think he was killed, no?
I'm not really up on this.
When I was looking at the big proof in Google, I found it about him, and I just read a little bit about him. I think he died some years ago, but or am I confusing him with someone? No,
Your challenge is to out-tweet him. Do you want me to say about lunch? I'll just say one other thing, that some of you might have noticed that whether it has lunch or included or not included in your package, for workshop